Okay, so we're going to start back up at question number 34. It says a typical bicycle tire inflation CO2 cartridge contains 12 grams of carbon dioxide. It has a volume of 10 milliliters and can inflate a bicycle tire with an internal volume of 0.914 liters to 92 psi. What was the pressure of the gas in the cartridge? Assume that all of the gas transfers from the cartridge to the tire. So we're starting out with our initial volume is 10 milliliters, and we're being asked what was the initial pressure. So we're looking for the initial pressure of the gas, this carbon dioxide, and it tells us what the final volume is. This is our V2, 0.914 liters, and it tells us also what our final pressure is. So our P2 is equal to 92 psi. So this is another application of Boyle's law, which is P1 V1 is equal to P2 times V2. And we're going to be solving for P1, which is equal to P2 times V2 over V1. Our pressure is given in psi, but they've also given us a conversion factor, which is that 1 atmosphere is equal to 14.7 psi. And so for our P2, we're going to put that it's 92 psi. I'm just going to put the conversion all in here. So it's 14.7. What is it, psi per ATM? So I'll put that all in there in one shot. The V2 is 0.914 liters. And my final volume is 10 milliliters. I'll just do that conversion factor in here as well. 10 milliliters divided by, there are 1,000 milliliters in a liter. Let's double check my units to make sure I set this up correctly. So I have PSI canceling, milliliters canceling, and then I have my liters canceling. And so I should end up with units of pressure in atmospheres. And I've already done this one ahead of time. And you end up with your initial pressure is being equal to 572 atmospheres. And luckily, they gave us all the answers in atmospheres and not PSI. And so the correct answer is 572 atmospheres. All right, let's move on to the next question.
I just want a quick question.
Sure, go ahead.
So that like 12 grams of CO2 part isn't really important to the problem at all?
Not in this problem, not one bit.
Okay.
It's kind of put in there to throw you off, I guess, a little bit to maybe you think you needed to use the ideal gas law because you could determine number of moles or something, but no, not necessary. Okay. Question number 35. A gas mixture has a total pressure of 774 torr. So we have our P total. P total is equal to 774 torr. The mixture contains 56 torrs of oxygen, 145 torr of nitrogen, and 322 torr of helium and some fluorine gas. What is the mole fraction of oxygen gas in this mixture? Well, one thing that we know from Dalton's law of partial pressures is that we're able to determine the mole fraction of a gas in a mixture because we know that P total sorry, what was I saying? We have our P total, which is equal to the pressure of our oxygen plus the pressure of our nitrogen plus the pressure of our, what is it, helium, right? And we know that partial pressure of each one of these gases, okay? So say, for example, you wanted the partial pressure of oxygen is going to be equal to the total pressure, P total, times the mole fraction of that gas. All right, and so from that equation, we are able to determine the partial pressure of our oxygen. Because if we just plug in these numbers, 56.0 plus 145 plus 322 torr, that gives us a total of, oh, it doesn't tell us what the pressure of the fluorine is. Oh, shoot. Anyhow, I didn't even need to do that, did I? Sorry, Mr. Dion didn't do this one ahead of time. We're given the total pressure right here. So our total pressure is 774. You know, let me even write down here that we have some fluorine gas in there. gives us a total pressure of 774 torr. And so the partial pressure of our oxygen is going to be equal to the mole fraction of our oxygen multiplied by the total, and the mole fraction of our oxygen is going to be equal to our mole fraction of oxygen is going to be equal to the pressure of oxygen divided by the total pressure. So what's the partial pressure of our oxygen? Is 56.0 torr divided by 774 torr. And you can see that the torr units cancel, and I'm left over with 56 divided by 774, and that gives us 0.0724. So yeah, there we go. There's the final answer. Okay, let's move on to question 36. You have a 2.602 gram sample of a volatile liquid, and you put it in a container that's 225 milliliters, along with 4.54 grams of dry ice. The vessel is heated to 95.5 degrees Celsius, at which point the pressure in the vessel was 14,220 torr. Determine the molar mass of the volatile liquid compound. Well, what we need to determine are the number of moles of that compound, right? Because we know that the molar mass of this unknown volatile liquid, so maybe I'll put it here, we'll just call it the unknown, is going to be equal to the mass divided by the number of moles, right? It's going to be equal to 2.602 grams divided by the number of moles of that unknown. Well, what do I know based on the ideal gas law is that even though I'm mixing two different gases, right, the volatile liquid, in volatile, remember that just means that it gets converted to a gas really easily, that when I solve for the number of moles based off of my volume, my temperature, and my pressure, I'm going to get the total number of moles of gas, aren't I? Because remember, when I solve for the number of moles using PV is equal to nRT, it's irrespective of the identity of the gas or gases. And so if I have PV is equal to nRT, when I solve for n, I'm going to get the total number of moles, right, using PV over RT. I'm given the pressure in torr. I have to convert that into atmospheres. And so I'm going to put that in the numerator, 14,220 torr divided by 760 torr per atmosphere. I'm going to multiply that by the volume in liters, 225 milliliters. In liters, I divide that by 1,000, I get 0.225 liters. The gas constant, 0.08206 liter atmospheres per mole Kelvin, like that. And then my temperature, 95.5 degrees Celsius. I already went ahead and converted that into Kelvin. I got 369 Kelvin. And let's double check our units. Kelvin cancels out, liters cancel, atmosphere and torr cancel, and I end up with the total number of moles. So my total number of moles of all the gas particles is going to be equal to 0.139 moles. Now, what kind of gas do I have in there? I have two gases, right? I have my unknown, and I also have dry ice. What's dry ice? Hey, let me ask you, can anybody tell me what dry ice is? Does anybody know what dry ice is made from? Or what's it composed of? Not a trick question.
Isn't it carbon dioxide?
Yeah, it's just solid carbon dioxide, right? Dry ice is CO2 solid. Okay, and we know the molar mass of dry ice, which is 44.01 grams per mole. So the number of moles of CO2 solid is going to be equal to 4.54 grams divided by 44.01 grams per mole. So that gives me the number of moles of CO2, and I've worked this out, which is 0.103 moles. So the number of moles of my unknown is going to be equal to the total number of moles, subtract the number of moles of CO2, which is 0.139, 0.103 moles. And when you punch that into your calculator, you get, what did I get? 0.036 moles. Now I can take this number and plug it into this equation. I'm kind of running out of space here, so I'll solve it down here at the bottom, and I get the molar mass of my unknown volatile liquid is 2.602 grams divided by 0.036 moles. That gives me 72.3 grams per mole. I have my notes in front of me and it says close enough. So close enough to 72.2 grams per mole. So that's how you solve that one. So, you know, again, there's nothing really mega complicated here about the mathematical operations. It's being able to interpret that when you're given the volume, temperature, and pressure, and you solve for the number of moles of a gas, that it's irrespective of the identity of that gas, isn't it? Let's move on to question 37. It says here that sulfur trioxide can be removed from a gas stream, such as the exhaust gases of a coal-fired power plant, by reacting it with magnesium oxide. The reaction produces magnesium sulfate according to the reaction below. We have a beautiful balanced equation given to us, and what it's saying is, what volume of sulfur trioxide gas at 298 Kelvin and 0.832 atmospheres could be captured by 1.50 kilograms of magnesium oxide? Well, we're given the temperature and the pressure, and we're trying to calculate volume. For that, we could use PV is equal to nRT. Sulfur V is equal to nRT over P. But what are we missing? We're missing the number of moles of sulfur trioxide. Well, the good news is that they've given me the mass of magnesium oxide that I'm starting out with, and they've also given me a balanced equation. So if I'm starting out with, what is it, 1.50 times 10 to the 2 kilograms of magnesium oxide, let's do a little dimensional analysis. I might have to do it down here so I don't run out of space. I have 1.50 times 10 to the power of 2 kilograms of magnesium oxide. I know that in 1 kilogram there are 1,000 grams, and I know that the molar mass of magnesium oxide is that there are 40.31 grams of magnesium oxide in 1 mole of magnesium oxide. From my balanced equation, I know that for every 1 mole of magnesium oxide that's consumed, I also consume 1 mole of sulfur trioxide. If we work all of this out correctly, let's check. Kilograms magnesium oxide, grams, moles, cancel. I would be left over with the number of moles of sulfur trioxide, which is 3.72 times 10 to the 3 moles of SO3. Now I have the number of moles. So now I can plug that into my ideal gas equation, and I get 3.72 times 10 to the 3 moles of sulfur trioxide times the gas constant, 0.0821 liter atmospheres per mole Kelvin. I multiply that by my temperature, which is 298 Kelvin. I divide that by the pressure, which is 0.832 atmospheres. Look at this. All the units should cancel. Moles cancel. Atmospheres cancel. Kelvin cancel. And I'm left over with volume. When I punch all that spinach into my calculator, I get a volume of 1.10 times 10 to the 5 liters. And so that is my final answer. All right, we got 8 minutes left and we got 3 problems left. Calculate the number of grams of potassium chloride produced when 8.33 liters of oxygen gas is introduced or is produced at 33 degrees Celsius and 555 torr, given the following unbalanced chemical equation. So the first thing I need to do is balance this guy out. Why don't I rewrite it like this? So I'll put potassium chlorate. And this is a reaction we looked at, didn't we? In one of the lectures it came up, I know it did. Plus oxygen. Remember, always balance the oxygen last because it's by itself. So I have two potassiums, I have one chlorine everywhere. So if I wanted to have only two oxygens over here, I'd multiply that by 2/3, wouldn't I? Right, so I'd multiply this by 2/3. So then I multiply the whole dang thing, or sorry, no, my fraction is off, isn't it? I would need to have 3/2 here. That would probably make it easier. So then I multiply that whole thing by 2, and I get 2 potassium chlorates, produce 2 moles of KCl plus 3 moles of oxygen. There we go. All right, I'm going to erase the top line just to make things a little roomier in here. There's my beautiful balanced equation. Move it up here. And it tells us that we have the volume of our oxygen. There's the volume. We're given the temperature, and we're given the pressure. All right, this is just a gas stoichiometry equation. If we could figure out the number of moles of oxygen from our balanced chemical equation, we could figure out the number of moles of potassium chloride, couldn't we? And then from the molar mass of potassium chloride, we could figure out its mass. And so we're going to start out with PV is equal to nRT. We're going to solve for the number of moles of oxygen, which is going to be equal to PV times or over RT. We have our pressure in torr. So we're going to put 555 torr divided by 760 torr per atmosphere. Okay, multiplied by the volume, which is 8.22 liters. Gas constant 0.0821 liter atmospheres per mole. Kelvin multiplied by our temperature, 33 degrees Celsius. So that's 306 Kelvin, like that. Let's double check. Kelvin cancel, liter cancel, torrs and atmosphere cancel, and we're left over with the number of moles. The number of moles of oxygen is going to be equal to, did I do this one? Nope, that would be too easy. Oh yeah, it's equal to 0.239 moles. Okay, so let's do some dimensional analysis now. If we have 0.239 moles of oxygen from our balanced equation, we know that when we form 3 moles of oxygen, we form 2 moles of potassium chloride. And we know that in 1 mole of potassium chloride, there's 74.6 grams of potassium chloride. Look at this. Moles of oxygen cancel, moles of KCl cancel, and I'm left over with the mass of potassium chloride, which is equal to 11.9 grams. And so that is the final answer. Question 39. What effect does quadrupling the temperature, Kelvin temperature, have on the root mean square velocity of a gas molecule? This is one of the formula that is on your sheet, which is root mean square speed. Root mean square speed is equal to the square root of 3RT over molar mass. And so what's going to happen if I quadruple the temperature? Well, that would be like doing this. If you're comparing root, let me just copy now. Root mean square speed is equal to 3RT, okay? And I'm comparing that to root mean square speed is equal to the square root of 3R times 4T divided by molar mass. Think about it. what I'm saying is the molar masses of the gases are the same. The 3 is going to cancel. The R is going to cancel. So if I take the square root of the temperature versus the square root of 4 times the temperature, what's the square root of 4? That means that this root mean squared is going to be, well, I'll just ask you guys, who could answer this question? What's the effect going to be? Get back to my chat here. Square root of 4. It's going to double it, right? So we'll put here, since square root of 4 is equal to 2, speed will double. Okay? Nothing more than that. Nothing more than that. Okay? Another way of expressing these two equations, after I canceled everything out, would be saying the root mean square speed is going to be equal to the square root of t, and over here it's going to be root mean square speed is equal to 2 times the square root of t. And so the effect will be to double it. Okay, that's it. We're on the last question, which is it takes a certain amount of time for a certain number of moles of hydrogen to effuse out of a container. So this involves Graham's law of effusion. If it takes the unknown gas 4 times longer for half of that number of moles to effuse out, what is the molar mass of the unknown gas? Well, for this, we're going to use Graham's law of effusion, which is the rate of 1 over the rate of the second is equal to the inverse of the square root of their molecular masses, or their molar masses, mm2 over mm1. This formula is provided on your sheet. Let me double check to make sure I'm not misspeaking. Yes, this formula is provided. And so we're comparing hydrogen, which has a molar mass of about 2 grams per mole. I'll just shorten it to make this question short and sweet. What are we doing here? Right? We're saying that